Hello guys, welcome to C9.5 Reversible Reactions. In this lesson we are going to learn about what a reversible reaction is and what's this term called dynamic equilibrium. What does that actually mean in terms of the molecules? So what is it you need to know? Most of this is core content. You need to explain what a reversible reaction is and give a few examples. So we're going to look at those later on. There's some key examples that I'll mention briefly to you today, but then I will also go into them in a lot more detail in later modules. You need to be able to write the symbol for a reversible reaction, very easy. Describe how to change hydrated copper 2 sulfate to the anhydrous compound and back again. So anhydrous might be a word you've not met before. Anhydrous just means without water. And hydrated is the opposite of anhydrous, which means with water. So you need to be able to explain why anhydrous copper 2 sulfate can be used as a test for the presence of water. We're going to look at this reaction in a lot more detail in a moment. If you're going for the extended paper, you need to be able to explain why a reversible reaction never completes, and that's related to dynamic equilibrium. So all the dynamic equilibrium stuff, you need to really understand that for the extended content. So let's have a look at this reaction here. You're going to get a chance to do this in class if you want to. It will be on your menu of things to do. Basically, you're going to put blue copper sulfate into a test tube and clamp it. You're going to need a Bunsen burner. As you heat that blue copper sulfate, it is going to drive off the water because the copper sulfate, when it's blue, is hydrated. In other words, it's got 5 water molecules. Now you'll notice a little dot down here. That little dot means that these water molecules are not actually chemically bonded to this copper sulfate. They are just there. If we heat, we drive off that water will come up this delivery tube and land in the test tube below, and the color change will happen. You will end up with just anhydrous copper sulfate, which is a kind of grey white color, and your 5 water molecules will be down here. For every 1 mole of copper sulfate you've got over there, you'll have 5 moles of water down here. Okay, so let's have a little look at that reaction in more detail. So let's come back here. While this video is going on, I would like you to consider 3 questions. How do you know the reaction is reversible? What would you expect to see if you added water to just the white anhydrous copper sulfate? And when we add water to the anhydrous copper sulfate, the reaction gets hot. What does this tell you about the backwards reaction going this way and the forwards reaction going this way? Okay, so let's see this in action. So you can see that this is the same setup that we had in the picture in the PowerPoint. You can see the blue hydrated copper sulfate there. So for every 1 mole of copper sulfate, there is 5 moles of water. And you can see already, just by giving it just a small amount of heat, you can see that the blue color is starting to leave the copper sulfate and it is starting to go white. So if we, I can't zoom in, never mind. If we have a look here in more detail, you can see that the color change is happening. Now we need to give it quite a bit of energy, which implies that this forward reaction is actually endothermic. We need to put energy in order to make it happen, which would imply that the reactants on the left-hand side of our equation, that they have more energy than the reactants on the right-hand side of the equation. Now, as we drive off the water, I can probably zoom in if I do this. As we drive off the water, you can see that there is some water vapor here. And that water vapor is going up the tube and it is coming down here, and it is collecting in the delivery tube at the bottom. And that is why the color change is taking place. So if we scooch on, you can see here are the two products. So you can see what we started with was copper sulfate with 5 water molecules, or hydrated copper sulfate. You can see what we ended up with over here was copper sulfate, and then all the water was driven off. This one's got no water, it's anhydrous. And those are the differences. Now, because of this little reversible reaction symbol here, if we add a little bit of water to the copper sulfate, it turns back blue again. Now that it means that the reaction is going in the backward direction. It's going from this to this. So the blue stuff here was able to turn into the white copper sulfate and the water, and the white copper sulfate was able to turn back into the hydrated version of the copper sulfate. So I asked you to consider some questions. How did you know that the reaction was reversible? Well, how did you know the reaction was reversible? Because you had this symbol here. Whenever you see this symbol here, it means that the reaction can go in both the forward and the backward direction. What would you expect to see if you added water here? Well, it would turn blue again. And then if you heated it up, it would turn white again. And then if you added water again, it would turn blue again. So it's just forwards and backwards. And all it is the addition or the elimination of water. When we add water to the copper sulfate, the reaction gets hot. So we know that this way, the reaction is exothermic. Therefore, in the forward direction, the reaction must be endothermic. And there must be the same amount of energy changes that happen. Let's have a little look over here. I can show you for this reaction, blue to white, the reactant had less energy than the products. Because in the forward reaction, we get energy taken in from the surroundings. And that energy that we gave from the Bunsen burner has gone into the products. And then we end up with the white copper sulfate, the anhydrous version of it. But in the backwards reaction, when we started off with the white copper sulfate, we gave energy out to the surroundings. So the products, or the blue hydrated version, must have had less energy in it. And that's to do with the making and breaking of bonds. But you can see that our red arrows are exactly the same. All the energy that we put in, we get out again in the backwards direction. Now, this thing called dynamic equilibrium happens when the forward reaction is equal to the backward reaction. If we take the start of the reaction, for example, let's take all of our blue hydrated copper sulfate. Now, say we put it in a closed system where we have the same amount of water and we kept adding and kept taking away, or we took a different reversible reaction. You'll notice here we have 8 moles of reactants, whatever they are, and we have no products at the moment. Well, we start the reaction in the forward direction and we end up making some of our products, in this case 3 moles. So we've got 5 moles of our reactants and we've got 3 moles of our products. Now, dynamic equilibrium happens when it doesn't mean we're not making any products or we're not making any more reactants. What's happening is every time we get 1 mole over here, 1 mole comes back over there. And every time we make 1 mole of products, we make 1 mole of reactants. And the forward and the backward reaction are equal. At that point, we call it dynamic equilibrium. And if we zoomed in, we would see a lot of chemical change happening, but that chemical change would be equal in both directions. There would be no net gain or loss of products or reactants. And as you can see, that doesn't have to be equal. It doesn't have to be 4 moles over here and 4 moles over here. It can be favorable to the forward or the backward reaction. And we're going to look at how we shift the equilibrium point next lesson. So what our learning intentions say that we need to give a few examples of reversible reactions. Well, I'm going to give you three main ones that we will look into in more detail later on. This thing called the Haber process, we will learn exactly how this happens, but turning nitrogen, mixing it with hydrogen and turning it into ammonia is a really, really, really important reversible reaction for the chemical industry. Ammonia is used for fertilizers. Without ammonia, we would never have, we'd never be able to feed all the people on the planet. It's also used for things like cleaners and things like that. If we take sulfur dioxide and we turn it into sulfur trioxide, that is a really important step in something called the contact process, which again we're going to look at in much more detail. And that's the process of making sulfuric acid in the lab. And sulfuric acid is another really, really important chemical for the chemical industry. It makes detergents, it makes paints, it makes paper and all of those fibers, like in your wicking fibers. It's used in plastics, it's used in fertilizers, it's used to blow stuff up, in car batteries. It's a very important chemical industry. And the third one is in the limestone cycle, which is when we thermally decompose calcium carbonate and we turn it into calcium oxide and carbon dioxide. The calcium oxide is called quicklime, and we want to make quicklime because it's basically the mortar that holds bricks together in the building industry. We use it in the glass manufacturing, and we use it when we're treating wastewater and recycling that so that it can go back to the environment. So hopefully now you should have seen the experiment where we change hydrated copper 2 sulfate to the anhydrous version. You should be able to say that it's very important as a test for the presence of water, because if we have the white anhydrous copper 2 sulfate and we put it in the presence of water, then it will turn blue. So it's a very clear indicator of whether water is there or not. If water's there, it will turn blue. You should be able to write the symbol for a reversible reaction. It's this one here. And you should be able to give a few examples, so 3 in fact, and explain why this reversible reaction never completes. It's to do with dynamic equilibrium. So that's it for now. Next lesson, we will look at how we shift dynamic equilibrium. There are many ways. Okay, see you next time. Bye.